Good afternoon, everyone, and welcome to today's talk. This is continuing a series of talks in the talk series from the Center for Data and Computing, CDAC. I am Nick Veemster. I'm a professor here in computer science. You'll start to see more of me if you haven't already. I'm down on the second floor in the corner. Come say hi. In addition to being a professor in computer science, I'm also director of the Center for Data and Computing. You'll also be hearing a lot more from us as the term goes on with various activities and speakers and so forth. One of the things that we're trying to do, and hopefully looks like everyone in this room has noticed and is aware, is we're trying to bring some very interesting speakers and partners to campus to talk about applications of data science and machine learning to various domains. And today, we actually have three visitors, two speakers from Microsoft who are talking to us today about a topic that's very near and dear to my heart, which is application of machine learning and AI to computer security and network security. In particular, we have three speakers who work in identity security, looking at basically how do you detect unauthorized logins to computing platforms. So let me sort of introduce them in some order. I'll start in order of familiarity. So the way that actually this came about is, actually Daniel, if you might stand up since we won't see you otherwise. So Daniel Wood is a recent graduate in computer science at Princeton University. He was actually my undergrad. He did a pretty cool undergrad project looking at basically applications of machine learning to IoT security. Okay, and so look at all the great things that you can do with a computer science degree. Now you can basically join Microsoft and apply the skills that you learn and do really cool things with network security. Our two speakers are also members. Daniel's a member of their team. So Alex Weinert is the director of identity security at Microsoft. This team protects users from unauthorized access, as I said. And if you've basically signed into pretty much any of Microsoft's products, Xbox, Skype, Outlook, Office 365, which we use here, et cetera, Azure, you've basically been the beneficiary of Alex's work and his team's work. And Maria Puertas Calvo is a senior data science manager on the same team at Microsoft. And her focus is really taking in recent advances in artificial intelligence and machine learning algorithms and putting them into practice. And that's something that we care deeply about here at UChicago and at CDAC, is not just the foundations of the algorithms, of course, but also how do you make them practical? How do you put them into a real system to solve real problems? So I'm very excited to hear today's talk from Alex and Maria. And without further ado, I will turn it over to you. Thank you.
Sure, thank you. Got a mic.
Oh, yes, you have a mic.
Yeah, we can turn it off here. Is that thing off? Hey, I'm Alex Weinert. It's nice. Thank you guys for showing up. This is awesome. I'm excited to talk briefly about what motivates our work and try to leave lots of time for Maria to talk about the interesting data science that sits behind the work. What we do is effectively try to protect a rather large user base. So what's called one of the key metrics for any online service is MAU, monthly active users, and we are at about 1 billion MAU. And that splits up about 75% to our consumer businesses, which are things like Skype, Xbox, Outlook, Hotmail, that sort of thing. Minecraft, if you're into Minecraft. And on the other quarter of it is all of the enterprises. And so your university uses Office 365. That means actually all of you have accounts with us, right? So that's, basically our job is to prevent two things from happening. One is to prevent somebody else from getting into your account in an unauthorized way. And the other thing we're trying to stop is fraudulent activity in the system. So people creating typically machine-controlled accounts to do things like send out spam or in other ways exploit stolen credit cards, whatever. So I'm going to give you a quick primer on the threat landscape, and then I'm going to let Maria take over and talk to you about what we're doing about that from a computer science and data science perspective. So just very quickly, I'm old. And so in 1982, we had these things called war dialers. I don't know if anybody here maybe would know what a war dialer is, but I wrote a war dialer. I actually hacked into NORAD in 1982, got a call from a policeman, security policeman, told me to stop. The next year, we saw the first at-scale attack on distributed systems. Right? The 414 broke into about 60 systems, and the vulnerabilities were primarily centered in weak passwords. If we fast forward 36 years, right, what we have is most break-ins on distributed systems are centered around weak passwords. So the fundamental vulnerability hasn't changed much. The password is not a great mechanism for securing an account. And I'll go through some of the specific ways why, but when we go look at all the things you read in the news about data breaches and exfiltration of data and political manipulation and global security issues where governments are attacking governments, about 80% of these source to identity compromise. Right? So almost everything that we see out there is sourcing to identity compromise. And there's three primary mechanisms that drive this, and they're called breach replay, password spray, or we call them breach replay, password spray, and phishing. Breach replay is you reused your same username and password on more than one site. The other site got compromised, right? So if you had a Yahoo username and password a couple of years ago, you were one of the 2 billion people compromised in that breach, then your username and password was compromised everywhere you use them, right? And that reuse is about 60% of users reuse passwords. So it's a high vulnerability space. Password spray, I'll talk about why password spray is so effective, but basically it's because you're using the same password everybody else uses. And so they're very, very easy to guess. And then phishing is where if I ask you nicely, I send you a nice mail like, hey, check out this video, and then you go to a page and it requires a username and password, you will reliably enter it at about a 15% rate. So those are the three main vulnerabilities we see. If we look at work we've done over the years in this space, we've applied a lot of both machine learning technology and straight heuristics and simple things like rate throttling and detection to try to slow down the rate at which password compromise either happens or the rate at which it's effective. In other words, that it goes all the way through to an account takeover. We are really, at this point, really pretty good at detecting that there's bad activity on an account. Right? And if you think about where Maria and I started, we were not on the same team at the time, but a long time ago we were working on this together on 2 different teams. And we were dealing with about 100,000 accounts that were taken over every day. Right? And if you kind of come forward to now, right, 6 years later, or 5 years later, we've reduced that rate quite a bit. And we're actually down to about 30,000 a day now, even though the system has grown substantially. So like, yay us, right? But the problem is that even one compromise can be devastating. And attackers will take one account and start to leverage that to penetrate deeper and deeper into an organization. And we can talk about some of the mechanisms, and we will have some time for questions. But to give you a sense of how fast these things move, right? Usually once an attacker is in the network, they're starting lateral movement within a couple of hours. What we have seen is that domain control, which means total takeover of the organization, takes less than 48 hours, right? So one account is typically leveraged to get lateral movement started, and then what happens is you go from a low privileged account to your friend who's a domain admin, to their friend who's the global admin, and so on, right? And then once they're in the organization, this is staggering, right? Usually almost a year to get people out. And a lot of that's because people don't pay attention to telemetry and because attackers are relatively good at hiding their tracks. So I'm going to take you through 3 primary mechanisms of password compromise very quickly, and then we'll talk about some industry trends. So the 3 primary mechanisms, the first one I talked about was password spray. Your basic problem is right here. When we look at the passwords that are coming into the system that people are trying to attack with, this is because they're pulling histograms off of other sites like the Yahoo breach, and they're looking at what the most commonly used passwords are. So the most commonly used passwords are things like 1, 2, 3, 4, 5, 6, right? And this is one that if you look on your keyboard, you'll understand why this is, right? 1QAZ is basically just the column of characters on the left side of your screen, and you move over one column and you do it again, right? So users are not particularly motivated, like you as computer scientists and maybe aspiring security people might be, but most users are not motivated to really put effort into their passwords. And even if they do, the complexity rules we give them plus human nature, the anthropology of the situation, guarantees that they will start their password with an uppercase character. They will have 4 to 6 lowercase characters. They will have 2 to 4 numbers and an exclamation mark. It's like, it's not an underscore. It's not a $sign. It's an exclamation mark. And some number of you are laughing because that's your password, right? And that's super typical. When we look at a password spray attack, what I'm doing is I'm taking a list of all the accounts that I've found. So I can go to your university. I can break your university, I promise you. I teach this class to high schools, is how do you change your grade, right? As you start off, pull down the directory of all the professors or all the people you can in the university, and then go start playing through common words. So this very password broke a major bank in the UK about 4 months ago, right? So this one password took out 20 accounts at a major bank, right? Why? Because it's fall and it's 2019, and their rules require uppercase, lowercase, and numbers. All right, if you have expiring passwords, it makes it worse, because you're more likely to use periodic stuff. Our attackers are not rocket scientists, right? They get tools like this off the dark web, $50 in Bitcoin, you get this tool. It's going to punch in the popular passwords for you. You just feed it a list of accounts. The second major thing we get is breach replay. And the story I like to tell on this one results from somebody looking at me across the conference table and saying, my users would never do that. 60% of users reuse their usernames and creds, right? And if you think your users won't do it, remember the Ashley Madison breach, right? The State Department had 15,000 credentials leaked in that breach. 15,000 people decided that the very same username and password they used for their career and their work was a good one to use on that site, right? People will reuse passwords. We detect this at our highest, like this is the highest volume of stuff we deal with, is replay of credentials that have come through lists that are sourced. And we'll typically process 100 million-ish a day. We see spikes up to 300-400 million a day. This was recent news, the monster 773 million record breach list. This was called Collection 1. Turns out there were 6 collections. They totaled over 2.5 billion credentials. All right, so again, you don't have to be a rocket scientist, right? Feed me a list of credentials. I'll spit them back out into nicely categorized files. Good accounts, bad accounts, blocked accounts, and non-deterministic state accounts. And if you want to go buy some accounts like this off the web to try for yourself, right? Don't do this on your own machine, you'll get malware. But you can go out and search for buy accounts, right? And this is just one of the first ones that popped up for me. It happens to be Cyrillic. But if you go down through this list, you'll see that an account, a set of accounts, like 1,000 accounts, is about 13 bucks, right? They're easily available to the attackers. The third major category is phishing. Phishing is super, super effective. People just, it's curiosity. My mom, I talked to her about all this stuff, and she called me one day. She says, hey, I think I got one of those mails that you were talking about, those phishing mails. I'm like, great, just don't click on it, it's fine. She's like, okay, but what if I did? I'm like, oh, man. So, and I asked her, I said, you knew, why'd you do that? And she's like, I wanted to see what was behind the link. So this is why you click on phishing mails. Don't click on phishing mails. If you got something from your bank, quick piece of advice. You got something from your bank or Apple or whatever it is you're worried about, just go to the website and log in. Like, I promise you, any notification you're getting an email, they'll handle it at the website too. So just skip the mail, skip the link. This is a cute graphic. What is that telling us? See who's awake. What's that graphic telling us? Yes? Yeah, normal business hours. It's just a job. Except for this dude who's trying to make everybody look bad, right? Like comes in after hours. There's always one. So then you get, then some of you, if you're like hanging out with security nerds like I do, you start hearing stuff like, well, what about, somebody steals the database and brute forces it. And in these cases, your password isn't really that relevant. And the problem here is that this step here, which is build, buy, or discover your list of passwords, like HiveIBenPwn publishes a list of 560 million passwords that everybody else has tried. And if on this planet you are 1 in a million, there are still 9,000 people just like you, right? Or 7,000. So, the problem is that your creativity is not that good. especially in the face of rules. And so the bad guy's going to attack you, and for $20,000, you can buy a system that breaks 100 billion passwords a second. Thank you, Bitcoin, right? This is because of Bitcoin mining. The crypto operations are super cheap, right? So now we can buy essentially for, take a small loan out, right? And you can go and start breaking passwords. At 100 billion passwords a second, how long does it take you to break 500 million passwords? That's going to get you 70% of the users out of that database, right? So once the database is exfiltrated, you're kind of hosed. It doesn't really matter how long or complex your password is. The problem is that you've used it before. And complexity rules and length rules make it more likely that you've chosen a password that somebody else has chosen, right? So in terms of the length of a password, people talk about you should have a 16-character password. Not really. You should have a password that nobody's used before. And if your password is over about 9 characters, you're out of the range of most attacks, right? A brute force attack on a 100 billion guess per second rig is still going to take you 80 days. People aren't going to spend 80 days per account. It's too much time. I'm happy to share with people the research on this stuff. And then there's keyloggers, malware, that sort of thing. Yes?
I do have a question. You mentioned Bitcoin rigs.
Yeah.
Because they hash quickly make password cracking easier. Is that the implication?
Yeah.
Would changing the hash on a password that's like a more memory intense hash sort of be a deterrent?
Yeah, the issue here is, so you can generally make the hash operation more expensive, right? We're doing 43 billion operations a day. And so the question now is how much, and I'll put it in terms that an altruist can understand, right? How many more nuclear power plants do you want us to start up to be able to do that for you? And the fact is that because of the first part of the operation, the fact that there's 500 million passwords are known, because that list is so publicly available and it breaks so fast, that meaningfully, even if I go an order of magnitude faster, I'm not doing anything about that problem, right? So I might, and so I have a whole paper on this that I'll send you, but if you go up, think about it, there's 96 characters per position, essentially, addressable, if you're not fancy, if you're not a hacker. There's 96 addressable characters on the keyboard. And so what you're going to get for every character is 2 more, you get essentially, you need 2 orders of magnitude to make that count, right? 2 more orders of magnitude of processing power to make that count, or difficulty in the hash algorithm. And so you're not getting a lot back. You spend a whole lot of electricity and heat, right? Is a whole bunch of, Bitcoin is, by the way, if anybody is into Bitcoin, just be aware, it's really bad for the environment. Okay, and then just remember that at the end of the day, your password doesn't matter because you are subject to the $5 wrench, right? And so this conversation that we're having right now is the one on the left, and the practical conversation to be having is the one on the right, right? As at the end of the day, I will just, tie you up and hit you with a $5 wrench until you give me your password. All right, so I'm going to wrap up here in the next couple of slides. Yeah. The thing I want to kind of get across here is that attackers are adapting really fast, so the intensity level of these attacks is increasing quite a bit. And so this is a nation-state sponsored attack that we detected, and each of these mountains is a single failed password, right? So it's a hash of a password, and what we're doing is we're looking at 500,000 or so per day accounts using the exact same password and failing, right? So that's our attacker's account corpus. That's what they're working with. And then we're able to detect which, essentially, we can't see the password clear text, but we can tell that they're trying one particular password over and over again. And you can see these sort of spikes. Over here, they're like 1.8 million accounts in a single day with one password. But what's interesting here is they adapt. See how the spikes become more distributed and lower, and then even lower, and then almost flat? That's the attacker figuring out our algorithms, right? And trying to get underneath our radar. It didn't work in this case, but the point is that they're very attentive to what we're doing, right? Any data scientists in the room? Okay, yes, I hope. A couple. People are doing this, that's funny. It's non-determinate. Anyway, so we use, you think about the ROC curve, right? From a customer's perspective, this is what they're really dealing with, right? And so, you have you're sort of, everybody's happy when the floodgates are open, right? Users are happy, but they're actually dying, right? And then if you get up into that top left corner, you've pissed off all the bad guys, but not so much the good guys, right? And then as you go over here, you can just turn off the power and you have a perfectly secure system. No good guys or bad guys get in. That's a secure system, right? So people have to set these dials, and that's a huge amount of the work we do is trying to figure out where do we calibrate this to, right? Are we willing to say, make it so that everybody who tries to join Skype has to go through 10 hoops before they can start using Skype, right? So those businesses have a say-so. And when we work with corporate businesses, they have help desk calls, and those calls cost money. And then before I hand off to Maria, the last thing I want to say is emphatically, we need you. Like, this is a place where good computer scientists are making a difference in global security. This team has dealt with matters of, like nation-state on nation-state attacks. We have dealt with matters of significant global security. And if you let the accounts go, if you let the systems break, think about all of the things in the world that are at this point automated, right? Every company in the world is transforming itself into a digitally driven company that collects data about users, that distributes that data, manipulates that data, tries to create optimized experiences, tries to control everything from your home environment to the power grid to nuclear weapons, right? And it all starts at identity. So the stakes are getting higher, and we may or may not have had something to do with both of these cases, And so if you want a job that is like seriously impactful, right, or if you want to apply data science in a way that is having a really direct effect on the world's safety, it's not a terrible choice. 11:57 or 12:57, and I'll turn it over to Maria. Everybody, this is Maria. She leads the data science team.
Hi. Let me turn on my mic. All right, everyone can hear me. Let me grab the clicker. So that was an awesome intro. I'm going to try to make my talk as good as that, but I probably fail. So as Alex said, I lead the data science team. So my work is to actually apply machine learning and data science to detect all of those attacks that Alex was talking about. So all those malicious logins that come from users that have been phished or brute forcing attacks. So I've given a lot of very high technical talks and a lot of very non-technical talks because I also speak to customers. And I wasn't very sure what type of level should I go for here. So I'm going somewhere in between. But if you guys have questions, please interrupt me. And you want to know more technical details of how we do something, let me know. So this is the first slide that I show in this talk to customers. And I say, well, this is what vendors and companies tell you that AI is, right? It's like they just show you a cool picture of some future thing, but they don't tell you anything about what it's done, right? So I go to the customers and I say, well, let me show you. This is how machine learning is actually done. Right. So I just want to tell you a little bit more about what is it to apply machine learning in the security space, because it's a little bit different than to other problems and why, and what are the different challenges that we've face and how we've solved them. So one of the biggest problems, like Alex said when he set up the introduction for the landscape that we work on, is that we have a huge amount of data, right? Which is only the technical problems of processing this amount of data every day and running models and setting up the data pipelines for our engineering team is already a huge challenge. Most people don't have to deal with this. So we have 170 terabytes of daily authentications. That's huge. That's about 25 billion authentications per day. We have 1 billion monthly active users. They're logging into more than 1 million applications, right? And then we try to find the bad guys in that set, and it's way less than 1% of all those calls are the bad ones. So it's literally finding a needle in a haystack, right? Or basically, if you look at it from a machine learning perspective, you just say your classes are completely imbalanced. But why do we choose to use machine learning? We don't only use machine learning, but it's one of the things that works best for us. Reason number one is because it can adapt pretty quickly to different attacks. If we can actually find some of the attacks in the ecosystem, we can retrain our algorithms and reinforce it and make sure that the system is adapting as quick as the attackers. And then you can also create heuristic rules, but then with machine learning, you can build more complex model that captures the different correlations, interactions between nonlinear features, right? So that's another reason why we do it that way. So this graph is just an example. This is a pretty old slide, but I love it because it really shows how what I would call our flagship machine learning system works. We put ML, supervised ML in real time with the authentication. So at the time you're signing into your Microsoft account, like your Hotmail account, there is a classifier that takes hundreds of features and spits a score that tells how likely that authentication is to be compromised. And that happens in less than 10 milliseconds to make a decision if we're going to let you in the account or not. So the way it works is basically the top is what I just described. A user puts in their username and password, and we'll issue a verdict. Basically, after we threshold it, it's going to say yes or no, we're going to let you in. Or if it says no, we're just going to present you with a multi-factor authentication challenge. So then you might solve the challenge or not, or you just log in, and that's the end of the real-time operation. But then we log all that information, and then we go and label those logs. And what we're trying to determine is, well, was the login actually good or bad? So we add up a lot more data that we are able to gather after the fact. So things like relying parties telling us if the login was compromised or not. So what a relying party is really the application you're logging into. So let's say that a bad guy gets into your account, and we let him in, and then they start sending phishing emails, right? So then the email team, the exchange team, tells us, oh, this account was actually compromised. You let him in. So that's like one source of a label, right? That we can say now, oh, that login was actually bad. So that's one way we can get that. You can actually tell us as the user if your account was compromised. Or we can also get it from like different threat intelligence data we have and other algorithms that we run offline with way more data from the day, from the week, that let us make better determinations than we can do in real time, because we can run like much more powerful algorithms with much more data about the login, about the user, et cetera. So with all that data, we will label the login. And basically, we will just say, OK, we have our true negatives or true positives or false positives and or false negatives. We'll just put it in a data set of label data. And then every day, or sometimes even more often, we'll go and retrain our algorithm. And once it's retrained, it passes a series of checks, make sure that it's better than the previous one that we had in the front end. And if it is better, we'll deploy it in the front end. And that's the new model that now it's adapted to the most recent attacks. So that's how it works. And I've been working in that model for the last 5 years. And there's we've done so many improvements to bring it to a place where we're actually happy with the way it works. Yes, go ahead. Sorry, I forgot.
It seems like, how do you know a true positive is a true positive? So you have to assume that the information is complete. But confirming that something is, in fact, there is no evidence of misbehavior doesn't necessarily mean that it's a true positive, right?
So
that is a good account.
When we label something as a true positive, we know it is a true positive. We have, I'm going to go a little bit more into the labeling part of it. But in general, we may have false negatives that we don't know about. But when we label something as a true positive, it's generally a confirmed true positive. So it's either from the users themselves, or we run algorithms that we constantly measure the precision on them, and they're like really close to 100% precision. Okay, so the main learnings about how do you do ML specifically applied for security, and for a lot of reasons this is really difficult. But to me, one of the main things is domain knowledge. And maybe by the time you guys finish school, this is not, hopefully will not be that important anymore, because it's actually really hard to train people in like understanding how to build features. And there's so many new techniques now that you're able to just feed a lot of data without really knowing what it means, and like have a good classifier for it. I don't think we're there, at least in the security space yet. I don't think models are able to make sense of just like random network data or random authentication data, unless you're codifying features the way that a human analyst will see it. The fencing layers has a little bit more to do with not just use machine learning, but like build different heuristics and layers and allow for self-reporting. And I'm going to go a little bit into that. Label data is very important because in security, as opposed to other problems, the attackers just don't knock on your door and they tell you, hey, I hacked this account yesterday. This is your true positive. Go label your data, right? So the way, like what I'm talking about, the way you actually get these labels to, if you want to build supervised machine learning, you have to get super creative. You have to also be comfortable with some noise in your labels, and like not everything's gonna be perfect, but you have to go out there and figure out how to get them. Yes.
How important are the labels? 'Cause, in my previous experience doing some of this, you can basically rely on, in many cases, on anomaly detection because the attackers behave differently than something that looks normal. I mean, I imagine based on what Alex said before about adaptation, that may be tricky, but
Yeah.
How much can you rely on unsupervised and not outlier detection?
So we do both,
Yeah.
definitely. But ultimately, you're going to need label data in order to measure the performance of your algorithm,
Yep.
right? Like you could say, okay, sure, this is very good at detecting anomalies, but are those anomalies actually bad guys that I'm looking for, or am I detecting anomalies that are false positives?
Yeah.
So the labels you're definitely going to need, some in order to always measure the performance. And then if you want to train classifiers, if you want to make them supervised, then we run a combination of both. But obviously, for supervised, you're going to need them. And finally, like related to what I was just saying, we're always measuring everything that we're doing. Like customers are actually the subjects of our models, and like when Alex was talking about the ROC curve, it's obviously really important that we don't challenge or block our users. Usability is a huge, huge thing to take into account when it comes to its balance with security, right? So we're always measuring what is that balance and that threshold. So just a little bit deeper into each of those things. The first one, when I was talking about why domain knowledge is so important, I think this picture illustrates it pretty well. So this would just show like a dummy example of logs. They will be from a user called Alice. They're about like March 3rd to 5, and then if you think about that real-time classifier, they will be evaluating every single one of these lines as an individual sign-in, right, that they need to make a decision on. So if you just took, let's say, if you look at it, like, can you tell me, like, if you see something weird in there? Something that might at least,
A new app called Xhang.
She's not SharePoint.
Yeah, that's a typo. But yeah, sure. If that was actually the data,
It's actually not too far off of what happens, though.
Yeah.
I mean, the Russian login is a little suspicious
Right.
as well.
So the way you're able to tell me that, because it might be, right? I'm not saying it's that one, I'm just asking. So you're able to tell me that because you see that Russian login in the context of the other logins of the user, right? So you're basically performing anomaly detection in your brain. But the user, the actual log that comes, that the actual information that gets logged when the authentication happens doesn't know the history of Alice's logins, right? It's just going to see, for example, 2:04 a.m. in a Linux machine logging into SharePoint from a Russian IP. So is that weird? Well, in the context of all authentications, it doesn't have to be unless you compare it to the history, right? So this is what I'm talking about when I say, okay, when you're building features for your machine learning, you need to understand from the perspective of like somebody who understands security, what does it mean to for how do you make meaningful features that are going to discriminate good versus bad, right? So you start looking at things like, oh, Alice doesn't normally log in at 2 in the morning. She normally just logs in on like normal work hours. This is not a familiar device for Alice because she's normally on Windows and iPhone. And this is not a familiar app. And look, not only she's logging in from Russia, which is an unfamiliar country for her, but also because I have 170 terabytes of logins a day, and I can see hundreds of millions of people. I know that there are 132 other users in that very IP address that are coming from different tenants, and maybe 90% of those don't have the correct password. So that gives me a lot of high altitude information about what else is going on in the ecosystem that I can encode into my features, right? So now instead of using this as my entry to my model, which my model probably wouldn't be able to do anything with, I'm going to build my features this way. So I'm going to say, is this a normal time of the day for Alice? False. Is this a familiar device? False, etc. I can bring from other algorithms things like, what is the IP address risk score? Because I have already evaluated the risk score of that IP address using another algorithm, right? And maybe stored it in my cache. So this is the stuff that really works well. And with this, you can just do anomaly detection, or you can actually use labels and feed it to a classifier. So, any questions about featureization? Okay. So number 2, we talk about defense in layers because when we embark in a new project, for example, we came from defending the consumer accounts, and we moved to now we're doing a lot more work in the enterprise accounts. We never really start with the machine learning models. Because we don't have labels, because we need to better understand the ecosystem, right? So we start with heuristics, and we build defense in layers. And when we talk about layers, we also talk about the different phases of protecting the account. So we have prevention, which is like that model that I was talking about earlier, that runs in real time with the authentication. So you can actually stop a bad login when it's happening. But we don't stop at prevention. We also do detection after the fact. So maybe even if we let a bad guy log into your account, we're still running algorithms like daily, monthly with aggregate data, and we may find things that we didn't find in real time. And then we're still going to say, oh, your account was actually compromised. So that's like the second layer that we make sure that we have detection on. And then for that, we use heuristics, but we also use different parties' intelligence. So like the example of the Hotmail telling me that somebody logged into your account and sent spam, that would also be fed into our detection phase. And then finally, we also make use of the remediation and mitigation stage. So this is us learning from what happened after we actually actioned in your account. It's very valuable information. For example, if on the prevention phase, I say, oh, no, I think you're bad. Here's an MFA challenge. But it was actually you, and you go and solve it. We say, oh, we were actually wrong. So that's a very good source of information that we feed into our model. Same with if we make a user reset their credentials, we can measure, we can observe the activity that the user did before or when we thought the user was compromised and after the user recovered their account. If there's matches in that activity, we actually can figure out if we were wrong or not. And then user feedback, like we always let our users or admins say, oh, this was compromised, this was good. So this is also something that will feed, right? So once we have all that, we build the machine learning phases, because basically we can get labels from all of those things and then feed into the previous phases from the posterior phases, right? So the real-time ML is basically the last thing we build, because we have all those different data labels and data points that we get from the posterior layers. Totally run out of air. All right, so then the next part is, and I've mostly talked about all of this through the talk, but make a little bit of emphasis. And the reason why getting labels when it comes to security is so hard, it's, well, the imbalance of classes. I think it's like looking for a needle in a haystack, right? It's really hard to, you can't just get a random set of data and get it manually labeled and get a good label set, because you're only going to find like 1 in 10,000. So the way, the thing is, we have to go out of our way to find this good set of labels, right? So one of the things we do is like we leverage those heuristic detections, because we can say, okay, I could either make a detection that I know is like 100% precise, so I use that as labels and like hope that my machine learning is going to find like a larger set of data and it's going to generalize more over the whole set. So that's one thing. Another thing is that maybe if you have a broad detection, for example, if I say a user has never logged in from this city before, maybe that's already narrowing my data set to something much smaller, where the balance of classes is going to be a lot more leveled, right? A lot more balanced. So then I can go and like manually try to find my label set within that stuff. So those are kind of like stratified sampling techniques that we have to use to find those labels. But how do we find them? So, well, this is just, I'm just going to go on this side first. So we get them from feedback loops. So the user, the admin, tells us this, my account was compromised, my sign-in was compromised. Or sometimes we use, for the enterprise case, we'll have like security operations telling us, or even people, investigators in our own team, they said, oh, I found an attacker doing all this bad stuff, then we know that was a compromised account. Customer support and dedicated human labelers. So this is actually what we're actually doing. We have a group of people whose only job is to, look at totally anonymized sets of data and like making decisions and tell us like what accounts are compromised and which ones are not. And this is how we ultimately measure the quality of all of our algorithms. And lastly, it's auto-generated, right? So if I can create a heuristic that has like a 99.9% precision, then I can use that to label my machine learning algorithm that hopefully will get me a higher recall with that. We use those labels to train models and obviously to also measure the quality of our algorithms. And that is my last point. Always measure. So this is something that we take very dear and near to our heart. There's a lot of people we talk to that even in other companies, or that they build an algorithm and they just test it with some, they partition the data test set in the experimental mode. It works really well, and then they just deploy it, put it out there, and they have no idea how it's doing. And they only anecdotally say, well, if we don't get too many customer escalations, it's okay. But we don't like doing that. We actually want to make sure that when Alex was talking about he had the opposite ROC curve, right, with the true positives, but obviously it's ultimately the same thing. If you just want that balance between usability and security, and we need to totally always understand where we're putting our thresholds and how many bad guys we're stopping for how many good guys we're actually putting friction on. And that is a super important part of our business, because the different organizations that we're protecting, if we start just blocking everybody, they're not going to like it because it's bad for them, right? So that's a very important part. So we use, with our labels, we always measure precision recall, volume of detections. We look at daily dashboards, and we're always adjusting to make sure that we are always at the point we want to be operating. So that's basically it. It's just a summary. Domain knowledge, super important. Defense and layers, how to get label data and get super creative, how to get super creative for that. And finally, always measure the performance and making sure that everything we're doing is working the way we want it to work. So I think that's it. So I think we have some time for Q&A now. I think Alex had to step out. We're having some work drama today. It never leaves you, no matter what. Yes?
I was wondering, over the years, has the nature of the attacks changed in such a way that you needed to update your feature space or acquire new domain knowledge to make useful features? Or has the nature of attacks remained pretty consistent over the years?
I would say yes, we've found some new attacks, some new MOs that for sure have we've had to add features. I think that we've also evolved to, so when I show you that first picture of how the whole model cycle works, our idea when we started with that years ago was we're just going to retrain a model every single day, deploy it out there, and make sure we get new labels every day, and we're totally adapting to the new trends. And then my take now is that because it's actually really hard to get quality labels, and I think that by doing that it was working out well, but the labels that we can get on a daily basis, they're actually just the low-hanging fruit. They're not like the more sophisticated attackers. So it's better to find a good comprehensive set of labels from a longer period of time and really understand what features you can build that are robust to that type of adaptation, right? So if you can say, okay, an attacker can adapt all these different ways, but this set of features is never going to be, they're never going to be able to beat that type of feature because, you're almost never going to be able to come from the same IP address as the user normally comes in from, or things like that, right? Then it just becomes more robust to just make sure that you have more comprehensive features that you don't have to retrain the model that much.
Can I have the mic for a second?
Yeah.
That's on this side. Okay.
Yeah.
So you didn't get a lot of into a lot of technical details because of time and so on, but I'm curious. I mean, you didn't talk about user behavior modeling, semi-supervised versus supervised, or a lot of these other things. But I'm curious as to, is there a clear dichotomy between the techniques that nation states use versus sort of common hackers? Because I would imagine that once you're at that level, the techniques should change. So presumably beyond just detecting thresholds and things of that sort, but things like intentional poisoning of classifiers using data manipulation on the training side, or sort of very sophisticated models on their end to really generate synthetic behaviors that mimic normal behavior in order to act as cover trafficking, those kind of things. Do you see that type of sort of distinctive separation between the sort of nation states versus everybody else?
Yes and no. Like the nation states use, that password spray attack that Alex was talking about. That they use, like, they go from like the cheapest way to the most advanced way, right? It depends who they're trying to attack. I think that in the end, even if you're a nation state, you're gonna just always choose the cheapest option available to you. And as long as people still have terrible passwords and they're able to log in, they're gonna go that way. If we detect it, it will be easier for us to detect it though. So we've also seen very specific cases through escalations and things like that where, nation state attackers go to do, they will like spearfish somebody and then make sure that they're logging in with like the same user agent, similar location, things like that. So definitely, as I said, when we we end up looking at the ROC curve, and we're always going to have false positives and we're always going to have false negatives. And nothing in security is foolproof. So an attacker is always going to be able to, spending enough time and money, get through your model. But to answer your question regarding like adversarial machine learning, and like we have not had the resources to look into that. But maybe it's something we can talk about later.
Thanks. You mentioned that there are always going to be like false positives and false negatives. I was wondering if you had a sense of how those sort of false positives and false negatives are sort of distributed, like with respect. So I'm thinking particularly like if you're not, say, in North America, are you much more likely to be a false positive or a false negative or something like that, or like how that varies and how you think about the trade-offs in those decisions?
Yeah, I think that there's so much work to be done there. A lot of our metrics, or all of our metrics, just end up being about the global data set, and then you realize that your global data set is not uniform. Mobile devices are way worse in terms of false positives because of routing of the IP routing of mobile phones. You just can come in from anywhere. So we're trying to invest a lot more in understanding device usage and giving more weight to if we can figure out what device you're using to make sure we mitigate those false positives. So that's one. In terms of geographical location of the user normally, we use a lot of behavior analytics, right? So like those features that I was explaining, I don't know that they vary much amongst regions unless you have unless activity frequency really varies, right? So for users that are also not very active in the environment, we're way more likely to also flag legitimate sign-ins as positives because the richness of information we have about that user is not as high. Oh, okay, so many. Go ahead.
Can you talk a little bit about how these systems can you talk a bit about how all these systems relate with the user experience and the priorities? You mentioned that this whole pipeline in real time takes about 10 milliseconds, like very quick. If that's not the case, if there's availability issues, at what point do you draw the line? Do you close the door? Do you keep the door open? And how do those decisions, I'm just curious like how those decisions get made between like your team and reliability engineers, product people, because that's one of the, I think, the thorn of your issues. Like, does an attack on availability actually open the door?
Yeah, that's a good question. So those questions are mostly, those issues are mostly decided by the engineering team. They're in charge of all that stuff, right? So we could say, okay, if this model is available or not, like we would just drop the call, or some of the decisions are, they don't fail the call, right? So you could say, if the model fails to evaluate, we just allow the call, or if the model fails to evaluate, we block the call. And I think we almost never block it, because you always want to have the system operational. But in reality, I'm not that involved in those decisions. It's like, that's mostly like a big engineering team decision, because they're the ones dealing with like, you know, it has to be less than 10 milliseconds, and it has to be up this much % of the time, and the failovers and all of that.
Is this on? If I can add to that, so I'm on the more product side of things. So one thing that makes this interesting is that we have to provide this data set and this risk score to customers that might want to act on it themselves. So depends who the customer is. If the customer is the State Department, they're going to have IT admins that are going to look at even low levels of risk and want to mitigate that. You have other customers that are very loosey-goosey. They don't really care who's accessing certain parts of their data. So we want to provide a tool that admins can pay for, that they can customize this based off of the analytics that we're providing.
Putting the diagram slide back up.
The cycle?
Yeah.
Oh.
Go.
And I actually had a quick question. So, in fact, perfect slide. You say that you have the very large set of logs that you could potentially train on. How much of that do you actually train on? Because per your earlier point, then you would imagine to get robust features, then just retraining day by day probably doesn't get you a lot. And you would also expect to reach convergence pretty quickly with the amount of data you're seeing.
Yeah, we definitely don't train in billions of logins. So for this system, I think we're using 500,000 logins for training. I don't remember what the size of the set is itself, but you're right. Like, you know, we're cutting it in width because we're featureizing it. This has a lot of data we don't care about, and also we cut it in size because we don't need billions of labeled data for training. Yeah, it's just like, you know, the bigger the number, the better it looks. Yes, Nick.
Related question. The slide you had on feature engineering, where you basically take the logs and then you sort of featureize those. Just curious, how much of that is automated? I imagine some of it is, but some of it isn't. Can you, where you basically go from, I've never seen this login before, or it's at 3 a.m., or this is a familiar piece of software or application or operating system.
Yeah.
You turn it into this nice feature vector. How much of that requires domain knowledge versus like how much of it is completely automated?
Well, the domain knowledge is it's used to figure out which data points we're going to look for familiarity on, right? Because something like, you know, like there are some things that are, I don't know if I can think of an example. I think every single column I put in this example, why can't I? Actually was used, right? Well, let's say like, you know, the session ID, right? The session ID is unique, so it's never going to be familiar. So you're never going to build a feature that says how familiar is the session ID. So the domain knowledge, mostly one part means like you understand what the engineering team is logging in your data and what it means and what things you can make use of. And the other part is like really knowing from looking at a lot of cases of compromise, how you can actually, what are the columns that you can actually extract valuable information from. And which ones are more useful or not. And this is a very dumbed-down example. We don't only say, is it familiar or not, but we also compute recency, frequency of all of those features, recency and frequency, and yeah, that's basically, and like count in general. So That's kind of like the part that we think requires limit knowledge, right? Like the user ID, it's always the same one, so that one doesn't matter. But the location, that one actually you really care about.
So the step on this slide from going from this to like the vector, it's pretty manual at this point.
Yes.
Required, yeah.
Yeah.
So you mentioned that you use you have some like auto-generated labels using some heuristic-based rules. So I'm just wondering what happened to the new attacks because don't have any heuristic on those attacks, right?
Yes. So what could happen is you don't detect it, or or your labels and your features, even with your like those are not our only labels. Just to be clear, like we understand that the ML is not going to give us much more if we're only training them with the low-hanging fruit. So that's why we also get labels from like the self-reported compromise, the threat intel reported compromise, and also our own manual labelers plus the heuristic one. So we try to combine them to make sure that everything is covered. If there's a new attack, the hope is that our features are robust enough that because we're using a lot of behavior analytics on it, that we're still detected, even if it's not like a common base attack. It's not from, let's say like all attacks, the majority of the attacks are coming from a certain set of countries, and all of a sudden we see an attack from a new country. Because we don't use the country itself as the feature, but we use how likely is this user to come from this country as the feature, then that makes it more robust to a new attack than if we were using the country as the feature itself, right? Because if you've never seen an attack from that country, your algorithm wouldn't think it's bad. But if you see, oh, this sign-in is coming from a country that the user has never logged in, I don't care which country it is, it's still gonna the model's more robust to that type of adaptation.
Okay, I think that's all the time we have, but we should thank Maria, Alex, and Daniel for the time today.
Thank you. Thank you all for coming. It was really an honor to speak to you.
So to your questions, I don't know if you have Twitter, but I put basically at the top of my link, I put the articles that I was talking about. And then I think it's safe to say I didn't get Daniel's. He can scribble it up if he wants to. If you have a Twitter handle. But if you guys want to reach out to us, we're happy to hear from you and answer any other questions or whatever. Cool.
Good turnout.
Yeah, great turnout.
Hope it was appropriate level of depth and inclusion.